de l'Université hébraïque de Jérusalem, we will welcome on stage Dr. Michal Sahaf. Her favorite subject was astrophysics, in which she won the National Olympiad in Israel. Fortunate enough to have received an excellent science education from high school up to her PhD, Dr. Sahaf is dedicated to offering young, talented people the opportunity to pursue their interest in science. Formerly working in a science museum as a science journalist, she now serves as the academic head and the physics lecturer at the Odyssey program in the Hebrew University of Jerusalem and takes part in the program aimed at encouraging girls to study maths and physics.
Dr. Sahaf will focus on the notion of the scientific method as being mankind's most recent, revolutionary, and powerful way of understanding the world. Using relevant examples, she will discuss what good scientific thinking is, the limitations and benefits of applying the scientific method to the phenomena we observe, and ways to use the scientific framework to better understand ourselves and improve our life decisions. Please welcome Dr. Sahaf on stage.
Thank you. Thank you for the kind introduction. So I have been asked to contribute a talk to this wonderful event about science, which I can do. I've done that before. I've also been asked to say some inspiring words to the young people here, something about your future in science. Now, I don't know if you've ever tried saying something about people's future. It's hard even if you know them, okay? It's harder if you don't know them, if there are many of them, and they're so different from one another and from me. So I'm sorry, Carlo. I'll talk about science. But then I came to think a little bit about, when I was a teenager, and I received some inspirational talks, and most of them sounded like this. Follow your dreams, use your gift, study science. I'm not saying this is a bad advice. It's just that when you go into the details, there's so many question marks. What is your dream? Is it your dream or somebody else's? And what's the best way to follow it? And what is your gift? How can you make best contribution? And how to use it? And study science, yeah, there's so many good reasons to study science. But which one is relevant to you? Okay, and which science? And what will you do after you study it? So I'm not going to offer you a lot of advice today, but I am going to try and offer you ways of thinking about questions, scientific questions, these questions as well. By the way, I forgot to mention, all the images that are not scientific were made with DALL-E 2, AI, artificial intelligence. So if you don't know what that is, Google it later, after the ceremony. So I'm going to be talking about the scientific method, and I will be using two examples. One is climate change. Everybody's talking about climate change, right? It's very relevant. The other is you and me, our lives, our decisions. There's a very big difference between these two. Okay? Climate change is something that anyone can measure, anyone with the right tools. So it is a subject for scientific research. You and me, our experience, our lives, I wouldn't advise you to try and write a scientific paper about your experience and submit it to a scientific journal. They will probably not accept it. Okay? So these two things are very different. But as a person who's been educated as a scientist, kind of soaked in science, what I see is that the scientific framework kind of penetrates the way I think about everything. And what I'm going to try and offer you today is an understanding of what we do in science. Now you probably think, yeah, I know how science works. So yeah, I'm pretty sure you know, but I'll try and break it down into points so we can really talk about it. And I will also try and show you how we can use these points to study not only things around us, which is science, but also ourselves and our interaction with the world. So when we talk about the scientific method, yeah, that's DALL-E 2 as well. When we talk about the scientific method, there's something that I want you to keep in the back of your mind. Look at this timeline, okay? It tells us more or less for how long we've been on this planet. So tens of thousands of years ago, people like us were living on this planet. And they were as smart as us. They were talking, they were telling stories, they were sharing ideas. But the scientific method as such, as a prevalent way of studying the world, is new, okay? So it means that it's less intuitive to us than talking or walking or telling stories. We have to learn those things too. So that means that science is something we have to learn, okay? It doesn't come easy. So just keep that in mind when we talk. So a scientific work usually starts with an observation. If we're talking about climate change, an observation could be your grandmother telling you that it is hotter now than it was when she was a child. Okay, so that's an observation. People have been making observations all the time. A scientific observation of the same thing will probably look like this. Okay, so here we see results from multiple sources showing that at the beginning of the 20th century there was an increase in temperature. Then there was a small decrease. People were worried about it, okay? They thought at the time that the Earth would cool too much. But then it started warming again, and now this is what people are worried about, and this is what is known as global warming. Okay, so we'll be talking about this. So what makes a scientific observation different from just any observation? We want it to be detailed. It's not enough to say that it is hotter now than it used to be. Okay? What does it mean? Is it that the hottest day is hotter than the hottest day before? What about the nights? What about the winters? And we want it to be accurate. Now, when we measure something, our tools will not be very accurate. They will have some errors, so we want to be able to estimate those errors. And we want it to be quantitative. Okay, how much hotter now than before? Now, let us put aside climate for a moment and talk about our lives. Observation is something that we all do. Okay, and observation can be something like, I did this project and I enjoyed it. At least I'm hoping you enjoyed your projects. I'm hoping you're not here because somebody forced you. Okay? Try and make it more detailed. What did you enjoy? Did you enjoy building something? Did you enjoy programming something? Did you enjoy studying something new and challenging? Did you enjoy it when people told you the project was good? Did you enjoy being praised for it? Did you enjoy working with smart people? Okay, try and make it detailed. Now, quantitative is not always easy when we're talking about our lives, but we can try and do that, like on a scale of 1 to 10. What did you enjoy the most? Or in terms of time, did you enjoy doing for like 2 hours a day or 10 hours a day? So we can try and borrow these concepts from science to our life, okay? It doesn't mean you can publish a paper about it in a scientific magazine, but we can learn how to use it. So the next step, once we have an observation, is the hypothesis. This is the story we tell, okay? We connect different pieces of knowledge by cause and effect. We're trying to say that this is the cause of that. And if we don't know where to look for connections, then a good place to start would be a correlation. Okay, correlations tell us where to look when we don't know. So a correlation means that we have similar pattern. For example, this is going up, and the other thing is also going up. Or we can have an anti-correlation. This is increasing, the other thing is decreasing. So if you're talking about climate, here's a correlation. The x-axis is the estimated number of pirates. The y-axis is average global temperature. And you can see that the more pirates we have, the lower the temperature on Earth is. When we have less pirates, and that's about now, we have a higher temperature. Okay, so there is a correlation. Well, correlation does not always imply causation, right? Either it could be a coincidence, or more often it could be something else that is causing these two. And I will leave you with the challenge of trying to find what is causing the extinction of pirates as well as global warming. When we're talking about a scientific hypothesis, it has to suggest a mechanism, and the mechanism has to make sense. It has to comply with other things that we know. So I also challenge you with trying to find a mechanism for the pirate thing. Okay, maybe the extinction of pirates does cause global warming. Okay, try and find something. I couldn't. A mechanism is not enough. We have to get the numbers right. Okay, maybe the mechanism works, but does it account for the warming that we see? Wouldn't it cause more or less? Okay, so numbers are important in science. And then it has to produce testable predictions, because otherwise it's just a story. Okay, and story is something that people do very well. But if we want the story to be a scientific hypothesis, we have to have ways of testing it. So here's another hypothesis you probably all know. Okay, we see a correlation between the concentration of carbon dioxide in the atmosphere and the temperature. They've both been rising. And we have a mechanism that you probably all know, and the suggested mechanism is called the greenhouse effect. We're getting radiation from the sun, and that is in many different wavelengths with a peak in the visible light, and that comes through the atmosphere and warms up the surface of the planet. And as the planet warms up, it radiates. It loses energy to space, so in this way it cools down. But it radiates mostly in the infrared light. And carbon dioxide and other greenhouse gases, they don't let that out, okay? They absorb infrared. And so cooling and slow down. And this is what is known as the greenhouse effect. So that's it. We've got climate change all figured out, right? We understand climate now. All good. Not yet, okay? A lot of people have been studying a lot of things and finding a lot of correlations. Some people have studying the sun, you know. The sun is very much related to climate. But not just how much energy comes from the sun, but also the magnetic activity of the sun. Okay, the magnetic activity of the sun has a cycle of about 11 years, and we see it changing through the number of sunspots on the surface of the sun. And it turns out that this 11-year cycle is not exactly 11. It usually varies somewhere between 10 and 12, and there is a very good correlation between the length of the solar cycle, which you see in red, and the temperature change. Or at least there used to be a very good correlation. Do you see where that ends? Recently, it became an anti-correlation. Oh, well, that's science, okay? Things are complicated. You think you have it all figured out, and then you find something that makes a total mess of everything. So it's not enough to have a correlation. Let's see if we can make up a mechanism. So how would the magnetic field of the sun be of any effect of what is happening here in the climate of Earth? It's a magnetic field, okay? It's not how hot the sun is. So scientists came up with a very interesting mechanism. The Earth is continuously being bombarded by particles, okay? Galactic cosmic rays, or particles coming from the galaxy, from events like supernova in the galaxy. And when they hit the atmosphere, they can stimulate cloud formation. And the magnetic field of the sun is like a shield. It can deflect them. So in this way, it can affect cloud formation. Most of you have been in the Science Museum a couple of days ago. Remember the cloud chamber there? You saw it, how these little clouds form as a result of particle coming in. So that's something very similar. Okay, there's the mechanism, right? Makes sense? So we would quite often have more than one mechanism that makes sense, and the whole thing looks more complicated than we would like it to be. And it's actually even more complicated than what I said. Clouds, do they make the Earth cooler or hotter? When you're walking in the sun and there's a cloud, you feel cooler. But clouds are made of water. Water is an excellent greenhouse gas. So having clouds is like having a blanket over the Earth. Okay, so it depends which clouds, where they are, how high they are, how they move. And actually, if you look at the whole thing, it's so complicated. Okay, it's not just the galaxy and the clouds and the sun and carbon dioxide. It's other things too. It's the trees that people have been cutting down. Trees take up carbon dioxide, and they cut them because they want to make room for agriculture, to grow food for people. And food includes, well, cows, beef that people like to eat. And cows, well, they fart. Cows fart. And their farts contain methane, which is a greenhouse gas. And there's the ice in the poles, and the way that the water moves in the ocean, and the way that the air moves around the Earth. All these things is so complicated. And we have multiple mechanisms. And that's when we come back to numbers. Okay, numbers matter. There's something known as climate sensitivity. I want to know if I am going to increase the amount of carbon dioxide, let's say double the amount of carbon dioxide, what will happen to the temperature? Okay, by how much will it increase? How sensitive is climate to any of those factors? Without the numbers, our hypothesis is not complete. And if it's not complete, we have to study more. So to learn more, we make predictions based on the hypothesis. Okay, predictions basically means what should happen under different circumstances, okay? Or where else can we see this effect? We can ask those questions, and then we can test the hypothesis. There are different ways of testing a hypothesis. So I'm going to go over these 3 ways, and I'm going to also mention how we can use them for our own study of ourselves. So, number 1 is an experiment. Number 2 is another observation. Number 3 is a simulation. An experiment is a great thing, okay? You build a setup, and you do whatever you want in it, okay? You have control of it, and you test whatever you want to test. The problem is that it is a simplified setup. So we have this Earth. It's very big, so it's hard to experiment on it. We also kind of want to live in it, okay? And if our experiment goes bad, then we wouldn't want to live here anymore, and we don't have another one. So we don't want to be running, and we cannot be running, experiments on the whole Earth. But we can build a simplified setup. So before I tell you a little bit about the kinds of experiments that can be done, let me go back to our lives. Experiment, is this something that we do with our personal lives, our personal decision-making? For example, when I was a teenager, and I was studying science like just for fun and reading, I thought maybe it would be a good idea for me to go to a science school. And this science school was actually a boarding school, and I was like 14 or 15, and that meant that I had to leave my family. It was a big decision. It was an experiment that I did in my life. And luckily, I enjoyed it very much, okay? It was a good decision for me. And then later, I thought, you know, maybe if I'm studying science in school, I would love doing it in university. Because in school, it was just a few hours a week. In university, it would be all day long, for years. So I would have a lot of fun. And that wasn't exactly the case, but we'll come back to that later. So, experiments, global warming. We could, for example, test how significant is the effect of this infrared light being absorbed by carbon dioxide gas. Okay, we can take greenhouse gases and see if they do the effect that we claim they do to the amount that we need them to do it. We can try and create clouds in the lab, okay, and see if the effect that we expect to get from cosmic rays is what we actually get. So this has been done, and this can be done and has been done. And there's something that I want to say about experiments, and that is that experiments don't fail. If they're good, if they're performed well, they don't fail. Even if they don't verify your hypothesis, even if they don't support your hypothesis, it's not a failure of the experiment. Okay, you have to update your hypothesis, yes. Okay, but you learn something. Every time you do a good experiment, you learn something. Same goes with me and my going to university. I learned a lot. First of all, I learned physics, of course. But I learned something about myself, the way I want to study. I realized that just sitting in class all day is not my way of studying. I don't enjoy it. It's not the best way for me to study. Later in my PhD, I could study at my own pace, read papers, take just a few classes. So I'm happy I did my degree in physics because it led me to where I am now, and I learned something. So that's important to keep in mind, okay? Your life experiments, if you do them well, even if they don't turn out the way you wanted them to, that's not a failure. And science experiments, the same. So another thing I want to tell you is that, you know, this is not what an experiment looks like. This mess is what an experiment looks like, with all the cables and everything. Okay, don't expect experiments to be beautiful. Nobody bothered to make them beautiful. I was a little bit disappointed when I first walked into an actual lab. So don't worry about it. And your projects, some of them are very beautiful and some of them just work. It's perfect that they just work. Okay, it's also very nice if they're beautiful. But they're doing what you wanted them to do, and that's what matters. So going back to our hypothesis. We want to test it. So another thing we can do is another observation, which means that we're studying the same system. Okay, if we're talking about Earth, it's this, Earth. And the problem is that we don't have any control of this system, and also it requires complex interpretations. Let's say that I want to study the past of the temperature on Earth. Before people had thermometers, how would you do that? You need to study it by proxy, right? You need to study something that indicates the temperature. So you have another hypothesis, like in between. So that makes everything complicated. What about our lives? What would another observation be in our lives? You don't change anything, basically, But you try and notice, okay? So if I notice that I like the challenge, studying something new and hard, do I like any challenge? What about sports challenge? And what do I need to make my challenge enjoyable and not just make me totally miserable? So an observation means that you kind of have new eyes. You notice things in a different way. So sometimes those new eyes involve digging into the ice for kilometers. Okay, and what we see here is hundreds of thousands of years of a very good correlation between carbon dioxide and temperature. And I won't go into the details of how this is being done. Okay, that's a little bit too much for the time that we have. I'll just say that it is done by looking for certain isotopes. Okay, water has oxygen in it, and oxygen has different isotopes, and they behave differently in different temperatures, and it's a good proxy for temperature. And you can see that carbon dioxide and temperature have been correlated very well for a very long time. Okay, so that supports our carbon dioxide hypothesis. But what about cosmic rays? Here we see, over hundreds of millions of years, the flux of cosmic rays, that's a yellow one, that can be studied using meteorites, and the temperature, that's a black line here, that can be studied using fossils. And these are in a very good anti-correlation. When we have low cosmic ray flux, we have high temperature. When we have high cosmic ray flux, we have low temperature. So this has been, looks like, it has been driving temperature on Earth over a scale of millions of years, okay? So that's the kind of observations that we can make, and there are many, many, many others. And last, a simulation. A simulation is a computer program, okay? And once you have the computer and you have the program, you can run it again and again, and you can change all the parameters, and you can play God, and it's wonderful. There's only one big problem, known as garbage in, garbage out. The computer only knows what you tell it. If what you tell it is not correct, the results you get are not correct. If what you tell it is incomplete, the results you get are incomplete. Do we do that in our lives? I'm going to give you a moment to think what that is. What is a simulation in our lives? Do you use computers to understand your lives better? Most people don't. But we do use this computer a lot, okay? We use it to visualize different situations, to think about the future, to plan, to daydream. Okay, that's a simulation. If somebody is asking you, what do you want to do next year, or in 5 years, or in 10 years, and you have an answer for that, the answer for that is a result of a simulation that you run inside of your head. Okay, me thinking that if I go to university, I will have fun, was a result of my own simulation based on what I knew at the time. Remember, garbage in, garbage out. Okay, imagination is a great tool, but it has its limitations. So I'm going to show you now a simulation of kind of the worst case scenario. Okay, it's trying to show us what would be the temperature, the increase in temperature on Earth at the beginning of the 22nd century, assuming that carbon dioxide continues to accumulate in the atmosphere. And it's using different assumptions here, so you get a very big range between 3 and 7 degrees. Okay, so 3 is bad, 7 is horrible. And so what is true? Okay, it really depends on the assumptions that you put in. So a simulation is a great thing, but we have to remember its limitations. So basically, this is a scientific method. You do it, and you do it again. You draw your conclusions, and you update your hypothesis, and you do it again and again and again and again and again and again and again. And some climate scientists will die before there's a full understanding of climate change. Okay, science takes time, and also our own understanding of ourselves. It takes time. But sometimes your hypothesis will be well established, and then you can call it a theory. And then the next step would sometimes be, not always, but with some theories, to take it out into the world, take action in a way. Okay, so it can be a new technology or new methods based on what we've learned, and sometimes government policy. And sometimes we don't have a fully established theory, but we still have to take action. Okay, for example, governments now need to make decisions about what we do with global warming. Okay, we cannot affect the galaxy or the sun. We can train pirates. Maybe training like 5,000 pirates will help. We can eat less cows and more plant-based food. We can use less fossil fuel and other renewable energy sources, okay? So governments have to make decisions, and people have to make decisions, sometimes when we don't have a complete understanding, okay? And same goes with our life decisions. Sometimes we need to make decisions, and we don't have a full theory. Now, I don't have a full theory of my own life. I definitely don't expect anyone younger than me to have a theory of their lives. I honestly don't expect people older than me to have a theory of their lives, okay? Because we are complex things, and we are dynamic things. We keep changing. Same goes for the Earth, okay? So sometimes it's very hard to know everything, but we can try and know more. So I would like to conclude with some science advice. I will try and make it both relevant to science, ordinary science, but also to the scientific way of thinking of understanding ourselves. Observe with honesty. Okay? Quite often there are things we don't want to see, or we overlook, perhaps because they bother us, or they look like something we're not used to. A lot of great scientific discoveries began with something that people overlooked. It looked like a mistake, it looked like noise, okay? But it turned out to be true. So start by being honest. You see what you see. Try to see as much as you can. You can later decide what to do about it, okay? But be honest with what you see. Be honest with your observations. Experiment bravely, but be careful, okay? Some of your experiments will have some consequences, okay? Definitely your life experiments, but also your science experiments. If you're working with people, if you're working with animals, think about the consequences of what you do. Yes, be brave, okay? If you don't do things, you will not learn new things. But try and think about consequences. A great way of thinking about consequences is simulations, right? So don't forget to keep updating your simulations. Don't fall in love with your old simulations, okay? That's something that happens to people sometimes, and they don't like to take in new data. They say, oh, this is probably a mistake. I will ignore this new data. Okay, so that comes back to, observe with honesty. And if other people have an observation, listen to them. Don't make fun of them. Listen to them. Maybe they're seeing something that you're not. And be open to changing your mind. People fall in love with their own hypothesis. Scientists get attached to their hypothesis. Okay, they get stuck in science, and people get stuck in life because we're not willing to change our minds. So keep in mind, your hypothesis right now is good. It's a working hypothesis. Okay, use it. But remember that it may not be perfect, and be open to changing it. And most importantly, be true to yourself. It is a scientific fact that every human being is a unique individual. And a unique individual means that we're all different. Okay? You're not your mother. You're not your father. You're not your best friend. You're not your sister. You're not your brother. You're not some role model you admire. You're you, okay? So you have your own perspective of things, and that is your perspective, and stand by it. I think it's very hard to make a good contribution, and it's very hard to have a satisfying life if you're trying to be somebody else. So yes, follow your dreams, use your gift, study science, but most importantly, be your own scientist, first of all. Okay, get to know yourself, because no one else is going to do it for you. I wish you a wonderful future, which means that even if at times you will not have success, at times you will not have fun, but I hope you find wonder in the world and in yourselves. Thank you very much.